Dieses Meeting wird aufgezeichnet. Haben Sie es verstanden? Ich habe es verstanden. Okay, welcome to week number 3. And still excited that so many of you are here. A little bit sad about the technical issues right now. Let's see how we can manage anyway. And I'm excited for a second reason. I'm looking for a person, Denise. Denise? You are not Denise, huh? But you talk to me, exactly. You are the one.
My first name is I have 2 names.
Okay. So this lecture today is dedicated to your question. This week was supposed to be special relativity and preparing for relativistic quantum field theory, but then there was this question about application to condensed matter physics. And this is not my subject really, but I saw that it fits in perfectly at this point. So I added one lecture where we apply what we just did with the raising and lowering. And it was really fun to work this out. So I wanted to have a topic that that is interesting enough, but that is also something we can do in 90 minutes. Something that uses the utilities and also that forecasts some features that we will encounter. So we can then look back. Oh, we saw this in this example. Like, where are the infinities? How does this wave function and the creation operate? And all of these things we'll see. So what I chose was superfluidity. The main chapter name is, I guess, an example. Second quantization. In condensed matter physics. And now here, an example. What's the example? Superfluidity. What is superfluidity? Naively, it's the flow of a fluid, liquid, without friction. It just flows. It's basically the analog of superconductivity. That's why there's a super. And the prime example that everybody mentions is, do you know perhaps which material shows superfluidity? Yeah?
Was it helium?
Exactly, it's helium. So helium, and there are different isotopes. They usually say helium-4, and if I say this, it sounds like I have any idea what I'm talking about. So it's the helium-4, the one with 2 protons and 2 neutrons. So it always has 2 protons because it's helium, and it also 2, so it end up with 4. And you cool it down because helium is normally a gas, and you have to go really, really low in temperature. So 4 Kelvin, it turns liquid. And it's like water. They clump together and flow. So liquid is, something that takes the shape of the container, but doesn't fill it necessarily, the gas fills it. So we have this liquid, and that flows with friction. If you go even cooler, then you go to 17 Kelvin, then it's a superfluid. And then you can stir it, and it goes on forever. It just flows. The 2 experiments they do is this fountain. Well, if you Google, then you'll find these 2 experiments. There's this fountain where you have this superfluid helium coming out. It looks fun, isn't really what I need. The other one is the creepy fluid. So you have a vessel, a container, and you have this liquid in there. And if it's cool enough below this is a bad vessel, then it creeps out. It attaches to the surface, and it just flows against gravity. And then you see it drip, 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 drip down there. these are the two experiments, and they exist, and you can look at them. I looked at them. It was hard to see, but fun. So you have this exists, and that is extremely special because normally you always have friction everywhere. You push something and it comes to rest. You don't really see Newton's third law. It is always something that stops. Newton's third law would say you go on forever, but there's force. You have this friction. It's just there, and the same is in fluids, and you have to go to extreme values to really see this. So it's the more natural thing is a fluid with friction, and this is the special case. If I come from the theoretical side, it's the other way around, right? If you write down a model, you start with the simplest, maybe free particles, and there's no friction, they just go. So if I write down the most naive thing, I will have a model for something that behaves like a superfluid, right? It's just the kinetic term, there's no friction. If I want the normal thing, I have to add stuff and work a little bit. This is what we're going to do. So I have a system with some interactions to model this. What we'll do specifically is we will find a critical velocity for the fluid. So you have your fluid that flows. We all go there with some, say, average velocity v, and we will find that's the specific computation we will do. That if that v is larger than a certain value, you'll have that friction. You lose superfluidity, and below we'll have superfluidity. This is just to tell you what we're going to do. This is what we are doing. We will compute this critical velocity beyond which this is broken, and we do this in a very simple model of hardcore interaction. So we have our particles, the fluid particles, and they are like free particles, nothing, no interaction, And if they meet, then they have an infinite force. So they can't, it's like billiard balls. They can't be at the same place or go through it. So that's the model. And then we'll find this. Right. We will start though by what's called the Landau condition. Which is basically a condition for, like, it's a rather naive, but still working argument for what is the critical velocity beyond which you have no superfluidity. And so Landau is a Russian physicist who worked a lot on these phase transitions, and you have the transition between liquid and superfluid, like ordinary liquids. And what's the argument? So you say your fluid flows with velocity v, and we say all of them together have mass. So this is the velocity of the fluid, and m is the total mass of this stuff that flows. And now we do energy and momentum conservation. So I assume that by interactions we will have some excitation created in this fluid. So let's say so. Well, what do I do? An excitation. Say excitation is created. Well, it carries momentum P, and if I want to do a little bit quantum language, I say it's h bar wave number. You know, this de Broglie wavelength. You know, it's the same as this thing, just with 2 pi's and rewritten. So the wave number or the momentum is same thing. For this argument here, it doesn't need to be quantized or anything. And energy, epsilon of k. And I'm not going to say how much this is. This is what I want to figure out. I'm just saying I have a excitation that has this momentum p, whichever it is, some value, and then it also has some energy. If it was a free particle, what would you think this energy is? Just give me a formula in terms of the momentum. If that's just a free particle, free excitation, yeah.
P squared over 2m.
Exactly, you just say this. But I'm not going to write this, I'm not going to put this in. Whichever it does, so this thing. Think of this is what I mean, or here h bar k all squared. Could be something like this. But I'm just saying that. And then momentum conservation. Says that the momentum before, that's the momentum of the liquid before I created this excitation, and then afterwards, well, afterwards I have, I guess, okay, and then this thing, because it gets a little slower, is the decrease in the velocity of the fluid, right? This is the decrease of fluid velocity. If I rewrite this, I cancel mv, this on the other side, so I have m delta v equals h bar k. So this was the p. That makes sense, right? So I have something that adds momentum. And so then this has to go down. I have a minus sign here, so this is a positive number. This is by what? This is slower. This is very, very tiny. Because this excitation is just one little atom. And this is all of them. So that is tiny. But still, just to have an equation that makes sense, I have to add it. If I didn't add it, then this would be zero and I can't create anything. So I have to at least have momentum conservation and then I get this. No matter that it is tiny, it's there. Energy conservation. Says, I have, here I'm using the non-realistic thing. I'm not going to have a super fast fluid. In fact, it should be very slow. So we have a superfluidity. This is before and after I have 1/2m now with v minus delta v squared plus whatever that is. UK. If I expand the square, I get this term on the left-hand side. I will subtract it on both sides. Then we have the mixed term. This is minus m times delta v. Then we have the square of the last. This is plus 1/2 m delta v squared. And then I have my epsilon. So we did say that the delta v is tiny. So delta v squared is even tinier in the following sense. I mean, I can't compare things with different units. I can't say delta v squared is smaller than delta v because it has units. Makes no sense. But v times delta v has the same units as v squared. And this velocity is whatever the velocity is, the microscopic velocity. This is tiny, and here we have tiny, tiny. So it's normal and tiny, tiny. So this I will neglect. Mr. Landau did that, so we neglect it as well. And then for m delta v, we just had an equation. M delta v is that. So these two together are h bar k. So what I'm getting is epsilon of k is equal to v h bar k. So this is a condition for what? If this is satisfied, then I satisfy energy momentum conservation when adding an excitation. If for some reason this cannot be satisfied, then energy momentum conservation forbids the appearance of an excitation. And if this is forbidden, then there can't be anything that slows us down. There's no friction. This is the superfluid thing. So if this cannot be satisfied, we are in the superfluid phase. If this can be satisfied, we are probably not, because then these excitations will be created, because they can be created. Now, what does it mean, can or cannot? Here's an epsilon. So we don't know how this looks like. But if this what does this look like? Let's just say you can't turn off the volume. Yeah, so I get all my emails. You can count how many. How does a dispersion relation look like? Let's use the example that from there, if it was this thing, then it looked like a parabola. And the right-hand side is linear in K with this prefactor, and then I have this line. And so, okay, boom, solution can be satisfied. Therefore, you will have the excitation created, and therefore there's friction in the fluid, and there's not. So this is the normal case. Can you think of a case where you can't satisfy? You know, I was talking about the critical velocity. If I turn this up or down, it doesn't really make a difference, because if I turn it down, I go here, then I have a solution. If I go really slow, I mean, or up here, it seems like I always have with this dispersion relation, I always find a solution here. You know, it's even worse. I usually want to stick with one-dimensional space, 1 + 1 dimensions, one space, one time, to have it simple. But let's say we live in 3 dimensions, like Landau did. Then he had a vector equation, so we had to have vector arrows over all this stuff. So vector. The k is also a vector. It's the wave number in that direction, and then and then you end up with a scalar product here. So then, really, in 3D or 2D, that you have, this is the absolute value. Or maybe your dispersion relation is not isotropic, and it really depends on the vector, but whatever. The energy is a scalar. This is h bar times v vector times k vector. So this is then h bar v times k, what we had, times the cosine of the angle between v and k. And so we have more to tune. To solve this equation, we can not only choose the absolute value of k, where it is here, we can also place it relative to the velocity. So in fact, what we really get as a condition is epsilon of k needs to be smaller or equal h bar v k. So what we had there in 1 dimensions becomes really this, yeah?
First of all, like these excitations, are these like phonons, or could these anything with ending with on be? What is?
Yeah, it could
Okay.
be. I think it is putting the particles in excited state,
Okay.
but we will see soon some quasi-particles, because we haven't even written down the model yet. So we will build the model out of 3 parts, particles that have this dispersion relation when they are free. Then we add interaction, and then we see that we get new particles, which then behave in a funny way. Yeah.
Okay.
And depending on what it is, they're called phonons. I'm not going to say this because I have no idea. Yeah, you see, this is we'll build this on bosonic particles. Usually, you have Well, the helium is fine, I guess. Yeah. Where are we? So this is the condition. So the picture then means if I draw that, so let me erase. I'm drawing the right hand side, the h bar vk. So this is a function of k with the slope vh bar, and this thing needs to be smaller or equal to this. So anywhere here is nice. If your dispersion relation, now for contrast in red, goes through here like this. You don't have to go up there. This would be in one dimension, but anything here can be satisfied by picking this k and having a little angle between b and k. So your excitation doesn't go in the fluid flow direction, but you can create an excitation a little bit at an angle and you satisfy energy conservation. So this is bad. This is a possible epsilon of k, and it is it will not be a superfluid because the excitation can be greater. If your dispersion relation isn't quadratic, so this is something like a squared, if it is this thing, then it will also be an ordinary fluid because you're inside. If you do this, yay. I mean, this is also okay. How do I write this? Well, this is the same thing, but it's not this the power that matters. Here it's the slope. This is outside, so there's no k. There's no k where epsilon of that k is smaller than h bar v times that k. So if we have a dispersion relation that looks like this, it's a superfluid. So let's write this. So I guess. Fluid, and these are no. And if you have something that just touches, bad too. I don't know. You go on my colors. You know, just touch here and then go and around. Then here you can solve it and you break down. You absolutely break down. Or if you do the other way, if you don't start with a triangle, start with your favorite dispersion relation, then you can put a triangle underneath. Say, put a triangle underneath. Where's my triangle? Zeigestock. So I turn and turn and turn until it somewhere touches. So here, this slope, this is the critical velocity. If it's below, I'm turning now this v number. If I take a very, very large v, large, I can at some point satisfy it. If I have a very small, then probably not. So this is the critical velocity. Here, slope is h bar v, and this is the critical velocity when it touches there. So that's what we're going to do. We're going to find the critical velocity in our model. Yes.
Just to be sure, like we get a superfluid if we don't have excitations?
Yes.
Okay.
Because then they move independently, all in their. I don't want to really say ground. I'll say the ground state. The ground state would probably be they all sit at rest, but here they move independently with this velocity, and there's no slowing down. Because there's nothing if yeah. So this is just the very naive here. First modeling of it. Yeah. And now we'll actually see this at work. Or something, hardcore interaction model. So a model where the particles behave like hardcore. Then I would write my potential of two particles. I'm back in one dimension, but I have two particles. It's a two-body interaction. We wrote it like this last time. And it should be zero most of the time, unless they are really on top of each other. So it should be a delta function. This is the potential. And now we put some number in front. The lambda is the strength of the core, basically. Also for dimension reasons, I don't want this naked, and the two will make some expression look nicer, I guess. Depends on nice. Now, how does this field theory Hamilton operator look like? So the interaction term, this V int hat in this many particle theory was the integral over x and y, and then the psi dagger x, psi dagger y, this two-body classical potential, psi x, psi y, operator. And this was the homework from last week email. And if I insert this here, I can perform one integration. Where was the delta function integration? First from last week here. You pick the y, I'll pick the y again. Then we set the y equals x, and we end up with integral dx lambda half psi dagger x psi dagger x psi x psi x. So this is the object. In terms of the wave function, now I want this in terms of the oscillators, but I'm not basing this model on the harmonic oscillator. This is what we did last week because it's so nice. You have this uniform or the spectrum equally spaced, and you have these creation operators even at the one particle level. Here, these are free particles. They should flow. Yes.
Oh no, sorry, no.
They should flow like a free particle, and therefore my wave function, the one particle stationary, the wave function, what's it called, the one particle wave functions of the stationary states. The solutions to the time independent Schrödinger equation for a free particle are, this is now a question for you.
E to the ikx.
E to the ikx, e to the ikx.
Divided by.
Well, now this is a good question. How are they normalized? If you allow x to be any real number and arbitrary, then they can only be delta function normalized, right? I want, for this purpose, if you've looked at the notes yet, imagine we are in a box. Well, really, it's one dimension, so we are just in it. We pick distance L and say we want either we just sit in this box, a little bit problematic for the fluid then to go past, right? How is it supposed to flow? So what you really should think of a periodic L wave function. We do quantization in the box, or we say we impose periodic boundary conditions on our thing. So then these modes K are countable. So blah, blah, blah. And then the next one, I guess. It doesn't really matter for anything. So then, however, the normalization is 1 over the length of the statement. Usually it was square root 2 pi. Depending if it stick in H bars or not. So this is the normalization. If we'll check it by taking so this could be labeled K, right? This has to be labeled K. This is the wave function with the quantum number K. So I want psi K complex conjugate psi L integral dx if and then I'm working in this box business. Now sticking these two in there, e to the I, the K has a minus sign, the L doesn't, and then I have a 1 over L. If they are different, this integrates to 0. For that to happen, they have to be quantized properly. And if they are the same, then you don't have an exponent. If 1 over L times this integral of L, so this is 1. If these things are the same, and 0 otherwise. So that's why I put the L here, the square root of L underneath, so this would be normal, this is normalized. It's really the least important and the least interesting of all this discussion, the normalization. So let's just stick with this. And insert it into the formula down here. My waveform. Oh, I have to now produce the field operator. So this is the sum over K and this psi, new page. Psi of X is the sum over all K's, psi K X A K. Do you remember from last week? Now we have the sum K e to the I K X square root L A K. And the dagger is the complex conjugate, and here's the raising operator. And the interaction Hamiltonian there is this lambda half integral dx. Now the first, well then we get, I guess we get 4 of them, right? 4 of these things. K, L, and N. The first one is daggered, so we have an e to the minus I K X. The next one is minus I L X. Then we have an I N X. Then we have an I N X. Then we have an A K, A L, A M, A N. And then the square root L with the 4. Just inserting that stuff. Integrating over our domain. Again, here in this exponent, we have K plus L minus M minus NX, same story.
Yeah.
If they all sum to 0, we have nothing there, then the integral is L. And if they don't add up to 0, but are quantized appropriately, then the integral is just nothing. So the integral with this turns, so the integral, we take the integral as well, the x turns into L times delta K plus L minus N minus N. Then interaction, lambda half. This is L squared times L, it's 1 over L. and then we have KLM, the sum over n, I'm going to perform by using this delta function, so the n is set to equal to this thing, and then we have an A dagger K, A dagger L, A nothing, M taking A, K plus L minus N. You still there? Could you see anything?
On the right side is kind of tough, but left side is all right.
If my cord was longer, I will put you in the middle, but it's not.
It's all right. It's all right. We can also
What I found.
look at the script.
Look what I found. I found an extension cord. All right. Let's try this. The interaction. How does the free part look like? This was h bar squared over 2m. Then integral dx dx psi dagger dx psi. This was the free part. Well, I don't know. Do I have to? Do we? Well, what's the time? Do we need to save some time? What? The derivative of this wave function acts here, so I get an I, get the sum over k, I k, and then all this the rest, e to the I k x squared L a k. This, so that's all of it. This is just the complex conjugate of it. Let's use the letter L. Minus IL, e to the minus ILX, square root L, AL dagger. The integral over those exponentials, we know by now it's the delta function. So we end up with h bar squared 2m. This is an L, which cancels the L from the integration. I times minus I, this becomes a square, so sum k, k squared, a k, dagger a k. Now we write this down in one line. But keep the headline. That's the model now. Our h is the h0 plus the h int, and just for completeness, all comes here, k squared a k dagger a k plus lambda 2l sum a l m a k a l a m a k plus l minus m. This is the model that we're talking about. It's the hardcore interaction model. The free particle with the normal dispersion relation, and then this interaction. If you set the interaction strength lambda to 0, you have this free model, and then you have just the particles with the normal Newtonian energy momentum relation. What I really would like to do now, but won't, it's too hard, is to find the eigenstates of this thing. And then what I really wanted to do, but certainly we're going to, because we haven't done anything, like we need the momentum operator. This is just the energy that now we would need a momentum operator, and we get a momentum for that state, the same thing. And then we express this E through this P, and then we have the dispersion relation that we're looking for. So that's what I would have to do. but nothing works. We haven't discussed this. We would need symmetries, Noether theorem, and what's the momentum operator? It really is just counting the one with just one K, but we'll see this. So first we ignore that. And this is too hard anyway for this entire H. And what people always have to do is some sort of expansion in something, and call this perturbation theory. So it's just a small deviation from the free thing by including this. You could say lambda is small, or what we are going to say is that the number of excitations is small. So we're looking at a state which is mostly psi zeros. So our state psi is something like psi zero, psi zero, you know, mostly. And then there's maybe some psi one. So it is going to be infinity. No, it's really not. It's n0 in the occupation number representation. It's n0 and then nothing and nothing and nothing, and or maybe one here. Let's just be modest, excite one by one step and then zero. This is kind of what I'm looking for. So this doesn't happen to be an eigenstate. I haven't tried, but that would be too simple. But something like this, a state that is mostly in the ground state with one excitation. Yes.
So in this case, like we have like hardcore interactions between the excitations. Am I like reading this correctly?
Between the particles.
Okay. So
Between two of the particles with this X and Y, it's gone.
okay. I'm not, then I would have to think about this, like this way of writing in this case. Because like we're not creating and annihilating particles correctly, we're creating and annihilating excitations.
No.
Okay.
These operators are the creation annihilation operators of particles.
Okay.
But then the whole thing, like this takes it away, creates it. So in total, it doesn't do anything really. But we are building it out of this. So even our Coulomb interaction, and it's it asks, this thing basically asks, hello, is there someone with this momentum? Is there someone with this momentum? Okay, then I'm gonna kick in with my interaction, but I'll return the particles with this. And we have to satisfy, that's a big sum. Basically, whenever you find two guys, you notice them, and then you say, okay, you interact. This is now the Fourier transformation. This is in momentum space. In the coordinate space, it was gone now. So then they interact, and they give you back all the possibilities, some of it K and L, two particles, and then you see this kind of scattering. The delta function was the momentum conservation in this interaction.
Okay.
But it doesn't remove or add a particle, it just adds the interaction, but using creation and annihilation operators that they do.
Yeah.
Also here, it just asks you, so the number operator gives you back the number of the states without stealing any or adding some in, but the counting works like go down and come up again. Yeah. Right. So we how do I write this now? We are thinking we are near this state, yeah. We want to be near this state where n0 is really, really large. N0 is about n. N is the total number of particles. I need more space to write this. So N0 is about N. These are the total number of particles. And this is the number of particles in the ground state. So would like to solve? But too hard. At least for today. And so we approximate our Hamiltonian by something. Whenever this A0 acts here, we're not properly counting, we just spit out N0. It doesn't matter if you have 1 or 2 here. N0 is like N, the A dagger and A operators are just the number N0 basically. So the expectation value of this is N0. Boom. We set this line here. Like this is an approximation, and we just set it. We're in some state, we're in a state, and these operators are these numbers. We're not acting there, we throw them out as quantum operators. These are just numbers counting the parts. And then, because I want to make an expansion in this.
Is it N0 or is it N?
It's N0 because I'm gonna. Same thing, right? N is N0 almost. I'll have in a minute, I have a subleading term. Let's do it now. N is the sum AK, all K. But this I can write as A0 plus sum over all non-zero K's. And I would call this the N hats. And this is the N0 number operator. I don't know, last time it looked like this. But now I think it's too small for a big number. So this is the number operator, but it's the same as the little one. So they are almost the same, right? Well, almost, because this is small, there's not much going on up here. This is Avogadro many, I don't know, 10 to the 23, and this is just 1. So that's the same thing. They're roughly the same here.
Yeah, but isn't the expectation value of A0 dagger A0 always N0? But we assume it's
Yeah.
going to be N.
Yeah, I'm an idiot. Exactly. Thank you for pointing that out. Yes, there's nothing now comes. What I'm doing is I say A0 without the expectation value, basically is. Of course, it's C. Yes, thank you. I'm going to replace this by N0, both of them, so I gotta go like this, and the A0 dagger comma, so both of them are replaced by this number, so it's not an operator anymore, and this is now not an equal sign. See, if I have a state with the number 3 here and then 0, 0, 1, blah, 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 and act with this combination on it, it's the same as if I just wrote n the square root 3 times square root 3. So it is the same on these eigenstates, on these states in the occupation number representation, but in general they can do also other things. But I'm going to replace it by this. I'm going to say that they are just numbers. And then I expand my Hamiltonian in large n zeros. It's all not really my idea, although I find it convincing. Now, where do we start? Kinetic? We'll start by the interaction term. So expand V int in powers of inverse n0. So the leading terms, what's the largest n0 we can get? Now we're going to look at these operators. So we have sum KLM, A dagger K, A dagger L, A M, A K plus L minus M. So there's a big sum, and if three big sums, and if any one of them is 0, then I get a square root n. So if I want really, really many n zeros, I better put them all to 0. And that works. If this is 0, 0, 0, then I have 0 plus 0 minus 0. So I can actually have them all 0. So all indices 0 produces n0 squared. You know, basically, because I'm replacing this. I don't know, equal or not. This is a term in there. So there's one term when they're all 0, and that is the leading term. That was easy. Now let's find the next one with the next largest number of n zeros, but with a little less fewer powers. So I guess not 4, but 3. So let's put 3 indices to 0 instead of all 4. What's your comment? Which 3? I guess put this, and this to 0, yeah? Exactly, because of the momentum conservation. If 3 are 0, then so there's no way that we can have only 3. We can't produce an n to the 3 halves. So it really goes down an entire n 0. So only 2. If we have these two 0, so then let's say two indices equal 0, which is then a well, it's I guess this. Let's start at the beginning. They are 0, and then what do we get here? What do we have to do with the indices? I guess not much, right? KL0, then we have M and minus M and minus M. Let me rename them so that I have a sum over K at the end. For some reason I like the K as a standard index. This is one term where they are 0. Now next one, which one? We have to see that we get all of them. So 0, 0. Then plus A dagger 0, A 0, A dagger, A dagger. What are we going to write for indices there? Let's say this is K. So I like the K. What's this index there?
Okay.
It's K. Funny, right? Because here we have K and minus K, and here we have K and K, and still it both means momentum conservation. Why? Because these are two annihilation operators, and you keep the total momentum the same if you take one with K away and one with minus K away. So that's why they have the opposite. Here, you take one away and we add one. If you don't want to destroy the whole thing, change the total momentum, then we have to take one with K away and add one with K. So it really makes sense. Now, let's keep going. Now 0, 0. A dagger 0, A, K. Now we don't even have to look anymore because now we know what this is. It's a K. Then we have a 0, and then we have a plus. Now we go to this. A dagger K, A dagger 0, A dagger, this is not I want to go here again. This is another zero, and then there's an A, K, two more. Plus A, dagger, K, A, dagger, zero, A, K, A, plus A, both zeros at the end, A dagger K, A dagger minus K, because, and then 0, 0. That's all we get. This is now N0 times sum. Shall we organize them a little bit? Let's do the one that preserved the number first. So we have KK equal A, dagger K, AK, and that is also here. So we have 2. It's here, so we have 3. It is there, so we have 4. And then we have 2 razors. A dagger K, A dagger minus K, and 2 lowerers. K, A minus K. Boom. There we go. This is now the subleading term in this 1 over N0 expansion.
What does A minus A mean?
What does, like this, A minus K?
Yes.
Let's say what is A mean? A is an annihilation operator that takes a particle away and it has an index. Why does it have an index? Because you have very many one particle states. And the index tells you what kind. It can all the A can only take a particle away in the state with that index. And the creator with the dagger creates exactly one like this. And the minus sign is just a minus. K is a sum. 1, 2, 3, 4. In fact, it is from minus infinity to plus infinity. So let's say K is 7. Then there you have a 7 and there you have a minus 7.
So we assume that we have negative excitations.
I didn't stress this. Yes, I do. Here's our one particle states, and K, if it's positive, goes this way. If it's negative, it goes this way. So I'm sorry, I should have really, because we didn't have this in a harmonic oscillator. So I know why you're asking. Now I know why you're asking. And in my head, it was clear, but it didn't really come out. Yes. The K, it also like the K is a it's honestly, it's a continuous variable, I guess, if our universe is continuous. Who knows? Then I did this business with the box so that I kind of count them. K is basically Kn. That's why there's a sum rather than an integral. Kn, and the n is like 2 pi n over L. These are the numbers, and the n is an integer. Yeah. So it really means take one away that. I was going to say take one away that moves to the left, but since I don't know what K could be minus 3, then it's one that could. Yeah. You can also go like this because the sum goes. Okay, now I've talked enough about the minus K. Where are did we write the free? No, we didn't write it. We haven't done the free part yet. In fact, I'm not happy with the interaction part yet. The interaction part so far in this expansion has this leading term n squared. So we have a lambda over 2L because that's what it was. There, lambda over 2L. Now comes an N0 squared and nothing. It's just the identity operator. Then we have plus still lambda over 2L. Now just one N0 and all this business. Let's write it down. 4AK, AK plus A dagger minus A minus K. And I really want an expansion in 1 over N in this number. rather than this. It's almost the same, but it has this subleading business there. So the n0 is the n minus the sum k is not 0. Who didn't copy this? And who wrote this? This is, I extracted all the zeros, so this can't be 0. If this was also 0, then we would get terms higher in it. So AK. So if I insert this n there and square it, then I get from the mixed term also something in this subleading. So this I need to take into account. So if I square this n0 squared, because it's squared, then I get an n0 n squared minus n times the sum k not 0 ak plus something of order n to the no power. There's also this square, it doesn't have any n. And this is correct up to order n0 to the power 0. We have the square, we have the 1, we don't have the n to the 0. And now I'm going to insert this here and this here and keep only up to linear in n. How does this work? The largest in n is, of course, this one. So I get lambda over 2l n squared. This is inserting this here, keeping the n squared. There's nowhere else an n squared coming, because this is an n squared, and here there's no n. So this is the only n squared term. Now linear in m, I get some. I get linear in m from the subleading here. Let's write this first. Minus lambda 2l n sum k 0 not 0 ak. So that's, oh, who did this multiplication? You did it because you forgot the 2, right? It's a square binomial formula, so it's a 2. I'm sorry, I forgot the 2. The 2. No, it's right, thank you. That's the linear and n term from here. And then there's a linear n term, and this is this n. Plus lambda 2l n and then sum k not 0 for a. This is a lot of writing. A dagger k minus k plus a minus k plus order n to the 0. Right?
Just a question, we're seeing what the contribution for the interaction potential is when we set a certain number of indices to 0.
Yes, that's what we're going to do. And I expand in this n. N is really large. So this term dominates all of this, and they together dominate all of this and so on. So I'm going to just throw this out. I could make myself super simple. I could make my life super simple, just keep this and say this is subleading, but that's a really boring theory. Then I have an interaction that is constant, and then okay, why are we doing anything at all? I want to keep something, the interesting bit. And the funny thing is that just keeping this quadratic part is enough to see our, what are we talking about? Superfluid breakdown, right? The critical velocity. It'll be enough. Well, 22. I can actually add the two together, right? The prefactor is the same. And then I have -2 and you have 4, so it's just 2 here. Our V interaction is this constant, the boring constant, plus lambda 2ln some k not 0, and I'll take the -2 in there, so I have 2 a dagger k, a k plus a dagger k and minus k plus a minus k. Boom. And if you want to remember this, it's just an expansion. Now we need the free part. The free part is super simple, because it is it was h bar squared over 2m sum k squared a k. So the ground state doesn't contribute even because they're just sitting there lazily. If k is 0, there's the 0. There's nothing, no contribution to the energy from the ground state. So I might as well just not write them. So this is done, expansion done. And these two terms together are now our model. And somewhere I wrote I want to find the eigenvalues, or eigenvalues, yeah. Eigenstates with the eigenvalues. The eigenvalues are then the energies, and see what the dispersion relation is. Is the dispersion relation in the triangle or outside? And yeah. And here, what are we having now? This is the kinetic part. This is just counting, it's quadratic, this is good. This isn't any worse. These two are really the same thing. I can actually, why don't I put them together? I'll put them together at some point. But this part of the interaction is just as good as here. It'll change the prefactor a little bit. These two, however, are annoying. I know which states are eigenstates of this, but I don't know here. I have to do some diagonalization. And a diagonalization here is called the Bogoliubov transformation. It's a transformation of these raising and lowering operators. So in the simplest case, you'd have an let's say you take a B and then take a linear combination. I guess I wrote it in the homework. This is not a little bit of homework. I'm taking this and replace it by B and B dagger. Have I done it this way or that way around? Nobody knows. Homework. Do you have your homework yet? I guess like this. And then the dagger. So example, this is not here. I didn't write indices. Example. Since this is the Hermitian conjugate, I have to conjugate the right hand side. So it's this plus beta b half. Now, in your homework, you will show that you can always redefine the oscillators without destroying this commutation relation by a phase. So this is one, right? This is what characterizes or the ladder operators, that their commutator is 1. Then this is the raising operator, this is the lowering operator. And that you can always redefine your oscillators by a phase. So multiply this by a phase. This is then multiplied by the conjugate phase. The conjugate phase is, however, the inverse, so it goes away. So therefore, you can argue you don't need complex numbers. This is enough if they are real enough, linear transformation with real coefficients. And then, if you want, then both the A's and the B's satisfy this thing. So that the B's are not just any operator, but number operators. Then you have to satisfy, am I going to tell you this? And a transformation with this thing is called the Bogoliubov transformation. It changes a set of oscillators into another change of oscillators. It's like an orthogonal transformation or something which diagonalizes your symmetric matrix, and here you have this oscillator algebra, and you get this, and this appears in many places all the time in this condensed matter business, and these are the traditional relation operators of the excitations that you started with, where you started your model building. You said, okay, I have these excitations which have an energy that is k squared times h bar squared over 2m, and then they interact. But the interaction changes the nature of the particles. If it's a small interaction, then okay, then it's just slight changes. If you do QCD, quantum chromodynamics, with strong interactions, then your fundamental excitations are something completely different, not quarks anymore, but protons, say. And there's even not a way to get there. Here, it's let's say we have a small interaction, lambda is small, and we have this expansion is all good. Then we still change the nature of the excitations, but we can actually compute it. So this is what's happening. This is what we started with, the free particles, and now we go here. We have this interaction and get to sort of effective excitation. I want to find their dispersion relation. Yes.
Are then in that case like B, like the B operator thing?
These are
Are these like creation and annihilation now for excitations? Is this then is now the way to think of it?
yes, but not sure if you mean
Okay.
that these are now the I'm tempted to say true particles. These are the excitations of that system
Mhm.
with a specific energy and a specific momentum, and you know, it's quantum world. You can superimpose everything and then it's all fuzzy. But if you're talking about energy eigenstates, something like that you want to prepare and can travel and you shoot it into an experiment, then it'll be these in the interacting theory. These will be the ones in the free theory.
Yeah.
Now, yes, I want to tell you one little funny story from another area in physics. If you do gravity, so quantum mechanics or quantum field theory in a gravitational field, you have something that's called the Unruh effect or Unruh. It's like a German name, but it's a Canadian guy. I guess he called it an Unruh. Unruh effect. And that is if you are in a or really Hawking radiation. Unruh effect is if you just accelerate. If you have an accelerated observer in a quantized theory, it suddenly sees particles. You know, there's nothing for us at rest. We are inertial observers. You just sit here and this is all the vacuum. And then there's someone who accelerates. And just because of his acceleration, he sees particles being created. Now you wonder, energy conservation, where are they coming from? Well, he's accelerated. He's putting energy into it and it's kind of slowing him down. And to keep the acceleration, he has to put more energy in. And so it all works out in the end. But like the vacuum state for us is one that is annihilated by everything, but the accelerated one has other oscillators, and so this is then for his oscillation excitable. Like the bees, his bees on this are not zero, so there's some stuff in there. And so you have a Liouvre transformation there too between an inertial observer and one that's accelerated. And since gravity and acceleration is the same thing, you have this at the black hole horizon or some, you know, black hole horizon. I guess you have it everywhere, right? But it's fun at there. Well, you don't have to have this. Like this Hawking radiation, some inertial observer that just falls in, doesn't see anything, but if you're at rest, you see stuff coming out of the black hole. And it's all just a transformation like this. So what what I'm really trying to say is, one of the fundamental questions that we always have to ask is, what are the objects that we're having here? And it really is observer dependent. Time. In this case, I'm looking for my, there we go. In this case, it's a little more complicated because we have all these indices. So our Bogoliubov transformation will also have to deal with the indices. And what is coupled? We want to really disentangle this. I want to end up like these two together, the H, I want to be able to write as blah, 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 and then dagger, be nothing. Like a free thing. And then figure out what's going in front. And there will be modes, K and K. And so the B's are also K's. And that's the same number of K's. I can treat every term like I have a big sum, which are actually coupled. If I take K equals 1, the simplest one, I have a 1 here, I have a 1 here, I have a 1, I have a minus 1. So if I say 1, there's also oscillator K minus 1 in there. And here as well. So then I to have all, I also should put K minus 1, yes?
What's the interpretation of B? Because as it's also just a part of the transformation, right, of A, or how can one interpret B? Is also open up
Yes,
creation and
yes.
okay.
These are then in the interacting theory, in this hardcore interaction model, these are the true effective excitations. They create the ones. They have changed their nature from what they were without the interaction.
through the transformation of A then.
And we'll see it through the transformation, yeah.
Okay. Thank you.
It really is, you're given a rigid body, say, in some awkward or non-appropriate coordinate system, and they give you the momentum, this Trägheitstensor, what's that, the moment, moment inertia tensor thing, and then you want to say, okay, what is this? Like, let me first put this in a frame with the main axes, and then I have numbers that characterize it. With this interaction here, I have basically a twisted system. I had here it's kind of the free model, and I know what I'm having, and now I add stuff to it. This is basically I start with a wheel, and I have my momentum of inertia tensor aligned, and now I put some crap there, and now it wobbles. And then I change it, and then I see, okay, I have these main momenta of inertia, and these basically I can read off there. It's going to say masses. Then I have lifted the degeneracy. Before they were the same, and now I'm diagonalizing this thing. So I want to say that this term couples positive and negative. This doesn't. So I really have to look at a sector. I can look at a sector. I don't need to look at the whole sum at once. I can look at a sector, but if I do it, I have to look at it positive and a negative K at once. And then the mixing will also mix positive and negative. So the AK will have a K here and minus K there, and then it's a K here and a K here and a minus K there. And this is what works. And you'll figure that if it didn't, you have to try something at some other transformation. In the homework, you'll convince yourself that this works. But let me, I guess, prepare it a little bit. Now, H is lambda n squared 2L plus lambda n over 2 sum. Now I pick K, only positive. Then I have. Oh, I'm making this too complicated. Then I have. I have what I have, AK. AK. But since the negative one isn't there anymore, I have to write it explicitly. And the negative one will be just this negative sign, A minus K, A minus K. And here, this is the same for the two. So I just get a factor of 2. A dagger K, A dagger minus K plus 2, A K, A minus K. So that is, I don't know. Looks like this, we have only the positive ones, but now we basically see what we have. We can diagonalize this better. The extra term is also there. And now for every positive K, we can look at this and apply this transformation. At some point, I need to add this kinetic term. Do I do this now? So I guess we have to first write it, x bar squared to m sum, let's say k is positive, then we have k squared a k plus a minus k, a minus k. So now I want lambda n squared to L plus lambda n 2, no, I want some positive. And now you figure out what is the field of k. If I go like ak plus a minus k, a minus k, a minus k. This one, and I figure out what is left. Plus lambda n, not even a 2, lambda n. A dagger 2. A minus k plus a minus k. So we're help. We need this coefficient, I guess, right? We need a bar squared, k squared over 2m to have the kinetic thing. And then we have this here plus lambda n. Huh. Let's see if I still. Yep. What happened to the L? What happened to the L? The L went on vacation there. So then we have an over L here and we have an over L here. This is my L, and now find 1/2 still. I'm having one second. So this is what I defined here in my notes. Okay, beautiful. Oh, are you solving my problem now? Yes, what's the question?
We square k, and we then only take the positive one. And we get it. No, it's not right.
I'm looking for it too, but no, because we had first all k's. And now I take only the positive ones, so I write these explicitly. This is basically the 2, the exogens. But still there's a 2 somewhere else floating around. Don't go. Okay, I understand this 2, and then I have dagger. Oh, this is just done. Okay, now comes something. This is also not really super necessary. If you want to perform the Bouguereau transformation for real, then you have to rewrite this in a number of ways and insert it and do things. So in my notes, I made this look more symmetric, but I got more terms. So, for example, in the harmonic oscillator business, we also had sometimes the dagger on the right-hand side. So I'm going to use a dagger A K is equal to, if I change it, I get punished by, can't just change them. There's what is the punishment for changing them? Help me with the sign.
1 minus.
1 minus,
One minus that.
like this?
No,
I wanted that
The
one, because I
one
want to
is-
insert this. Is it right? Plus or minus?
no, the 1 equals 1 minus,
No, like I think this is right.
is
Yeah.
it? Awesome.
Let's trust him, and if it isn't, then we blame him.
No, oh, sorry, it's the commutator, it's not that,
So
sorry.
I'm going to take half, I split this into half of this plus another half of this, and the other half I'm going to use this thing. So then, we get H is this awful constant, lambda n squared over 2L plus sum k larger 0, E of k half, and then A dagger k A k, but then the other way around, this thing, A K dagger. So that's that. This half, it pivots. And then we have the one with the minus k. So I get also A minus k plus A minus k with the dagger here. The punishment comes later. And for the interaction time, I write lambda n over 2L, and I do the same. I take half of this and then the other order, but there's no punishment because the A dagger with the A dagger commutes, so I get A dagger K, A dagger minus K, and also A dagger minus K, A dagger K, plus A minus K, plus A minus K, A K. Parentheses, plus punishment, but the punishment is a constant. It doesn't even depend on K. So all of them get a 1. So I get a sum over stuff. So I get here just a constant. And that constant is really infinite. It's an infinite constant because I have sum over all numbers K, all positive Ks. And that's what we always will find. Quantum field theory has infinities here and there and everywhere. And it's basically because you have infinitely many modes. And if you adjust this one little constant, you get punished for real, basically. And we have to deal with it and make sense out of this. If it's just a constant, then you say, okay, I set my scale to this constant. It doesn't make any difference. You just subtract it from the energy. You can't do anything with this constant energy there. So it's just going to be thrown away. Why did I write this in this complicated fashion? Because I had a minute. Now you can write this in a matrix form. You have left matrix, and then inserting this transformation will be simpler. This is the homework. And when you've done this, the diagonalization, you'll be guided through this. I have to take 1 more minute of your time. When you have done this diagonalization, your Hamiltonian will be some k not zero. Oh, not zero, positive. I took them back. Now epsilon of k, b dagger k, b k plus an awful constant. Everything that we neglected of higher orders, all the infinities that we got. But this is the thing with epsilon of k equals what we had is e of k, h bar k all squared 2n plus lambda n l this squared minus lambda n over l squared. And the picture of this object is drum roll, linear here and quadratic there. I'll discuss this more tomorrow, a little slower, but the punchline, we need to have the punchline. So if I expand this in small case, then I have to square and then I'll find that this is linear, and then for a really large case, you don't see the interaction, and it's just what we have. This square with this square root goes away, and the k squared there. So we have this dispersion relation, and now we put a triangle underneath and raise it as high as we can without allowing the dispersion relation to enter. And then we have a critical velocity, and that from here is the coefficient of this expansion in k. So this is actually equal to, you can expand this thing for small k, and you find square root lambda n. This is the square root nl, where you get the n from there. H bar k. So this is for k, small k. It looks like this. So we know that is the critical velocity, lambda n and l. If your fluid flows slower than this, then you cannot satisfy your energy momentum conservation. So it just flows without creating excitations, without slowing down. If your velocity is higher than that, then this is in the region you can create excitations, then you will create excitations and they will slow you down. Question, comments? Yes.
So I just want to sort of sum it up and make sure I get the right idea.
Yes.
So this sort of reminds me what we do for an atom when we're trying to solve the electronic part. So we sort of like separate it as the motion of center of mass of this whole mass fluid itself and what's inside.
Yes.
Right? That's what we did. And then what's inside is our Hamiltonian.
Yes.
And then the energy transfer between the two happen. And what we're saying is you can slow down the fluids by giving the center of mass energy to the inside as a creation of a particle. Is that what's
I think that's what I tried to say. Yes.
okay?
Exactly.
Because I was thinking if you were looking at it first in the rest frame, but then can one even talk about rest frames at non-zero temperatures?
Oh dear. Why not? If so, non-zero temperature, then you have many particles and randomness, but as a whole, it should have a center of mass, and if this is at rest, then you're in the rest frame of this. Some go there, some go there. But I'm not doing even temperature. See, there's also a little jump in the logic. In Landau's argument, we really had a fluid that flows at velocity v. And then in the next chapter, I came up with this model, the Hamiltonian with the interactions, and then we looked at basically the ground state. We just wanted to find the dispersion relation. And for this, you don't have to set them all moving. They were all in zero. They were all just sitting there, and we tried to create one excitation where everybody else was just stationary. It's not that in this chapter subsection 3.3, we had this thing flowing and then on top we created something. So they were all just sitting and we wanted to know what is, if someone wants to move, what is its energy when he moves. So when he moves a little bit, you get some momentum and then energy grows linearly with it. So starting from all at rest, it's basically just a model and find the dispersion relation. There isn't really this fluid flowing in the back. We don't.
But without it, how could we excite this?
Yeah, no, this is sort of a kinematic question. It's a Hamiltonian, and you find what are the states for this Hamiltonian. The
Yes,
real
but-
Hamiltonian was complicated, and then we just do the
Yes,
energy eigenstates for this thing. And then we know, oh, they exist. And then the Landau argument kicks in and you say, oh, if they exist, then energy momentum conservation. We don't see them created. There's no dynamics in here. We are not having a fluid that flows and then some Hamiltonian produces in a time evolution a creation. That's not what we've been doing. We have just a Hamiltonian and diagonal and find the energy eigenstates for this Hamiltonian.
yes, but isn't the fact that the fluid's moving is basically given possibility to excite the state?
Yes.
Okay. So,
Yes. Right. It's just
because otherwise the states are stationary, we would stay in the. Right?
Yes,
State or-
Yes. Okay, right. But what I was trying to say was that there's a difference between that story and what's really happening and this computation. In this computation, it really is just diagonalizing the Hamiltonian, finding the energy eigenstates. And there's no dynamics in here. It's just where are the boxes where I can put my particles, and they lie along here in this energy momentum plane. But then, given these
Yeah.
states in these boxes, what happens in the fluid then is they flow, then they collide because there's interaction, and then they occupy some of these states, and that is allowed by energy momentum conservation. So they do, and then the whole thing will be slower, slow down.
Yeah, I think I understand your point.
Yeah.
My,
But
yeah.
But that was just a story. I didn't do any computation that really shows that they're excited. It's just that there's some, in this model, there's something that can be excited. Well, what's really interesting is the free one was like this. It was just k squared. So there was nothing to hide underneath. And now with the interaction, it raised the dispersion relation up. And then there's something that can hide underneath. So in this regime, which speed slower than that, you cannot excite anything. And so then you say it flows like in the free theory. And if you go really fast, then you can excite the ones that exist. And then you see the breakdown of superfluidity.
What exactly is L in our picture? Because like I thought it was always just a help thing that we
Exactly.
like when you go to infinity.
You say N
Oh, I
over
see.
L is the density of your particles.
Okay.
Thank you. That was a good point. I mean, yeah, we should always go back and also look at the constants. Does it make any sense? What does it mean? Well, what's going on? What are the parameters I can tune? And here it's essentially the density of the fluid. Yes.
And if we interpret this L like how far the particles span, could we then also like, because it's the wave, right? Could we
yeah.
like interpret this as some like Coherenzlänge?
We were,
for
yeah,
ultra-
yeah, I know.
Like
I don't know. There's going to be another story at the very end. It's called renormalization. And when we start with putting some constants into the Hamiltonian, we have no idea whether they will have the meaning eventually that we planned them having. Like you write M, I write H here. This M, haha. I think it's a mass. But it doesn't need to be the mass of a particle. It's just a constant that's in there, and then we'll have to have a different definition that can basically measure the mass, and it's not always this. So even if there's a rho and an L, it doesn't need to be what we thought it was. This all gets renormalized, usually by infinite constant, and yeah. It's very interesting that these interactions can mess up everything, and I thought that's why I got excited by this thing. It's a sort of simple model where you start. You think of, you start with here, you add this, and then many things change. In particular, what is the excitation? What are the fundamental objects in your model? Yeah, thought that was cool. Wonderful. So I'll wrap this up by summarizing it one more time tomorrow, and then we move on to special relativity. Thank you. Okay, switching off.
Bye bye.
I